Okay, so the plate looks like this. So this is a two-dimensional problem, as you can see, right? So the plate width is 10 centimeters. So the distance here is 10. And this is kept at 0. This goes all the way to infinity. So temperature here will be 0. This guy here, the temperature of X is equal to X. Okay. So for example, at 2 centimeters, the temperature will be 2. At 3 centimeters, it will be 3, etc. Here, on this side, the temperature will be 0. And on this side, the temperature will be 0. Okay? And so this is a 2D problem. No? So Laplace's equation reads, so basically we're going to be solving Laplace equation in 2 dimensions. In 2 dimensions. It's d squared t is equal to 0. And the Laplacian, that's just d squared t over dx squared plus d squared t over dy squared is equal to 0. This is what we're going to be solving. Right? Yeah, so like I told you, we make an assumption. Assume, the first step is to assume a solution of the form. So that's the first step of the form t equals big X as a function of X times big Y as a function of Y. And then take derivatives and plug them in. That's the first step. So go ahead and get started on that. So we're going to take that to be our solution, and we're going to take the Laplacian of this and plug it in the original equation.
So the steady state distribution. Okay, so that basically means.
Yeah, the steady state means the right-hand side of Laplacian equation is 0.
Right,
okay. So here dt over dx will just be dx over small x times y, because y does not depend on x. And the second derivative will just be d squared x over dx squared, right, times y. So this will be the first guy there, and then we'll do the same exact thing for the y, and we plug them in. So dt over dy will equal x times dy over dy, and d squared t over second derivative dy squared is equal to d squared is equal to x as a function of x times d squared y over dy squared. And now let's call this equation A. So now we're going to plug these two in equation A. And so we're going to get d squared x over dx squared times y plus d, you follow, man? Dx times d squared y over dy squared equals 0. Okay, And now we're going to divide both sides. This is called now separation of variables in the method. You're going to separate the variables. So we're going to divide by xy, the entire equation. Okay, divide the entire equation by xy. So if I do that, then I will get 1 over x, big X as a function of x, times g squared x over dx squared, plus here if I divide by xy, the x will go away and I will get 1 over big Y as a function of y, times g squared y over dy squared equals 0. And this is the step where I can say each one of them has to be a constant. For this to work, right, these have to be constants. Okay. Now, at this point, of course, one of them, we can call one of them k squared, one of them minus k squared. The question becomes which one has to be minus, which one has to be plus. For that, we have to look at the boundary conditions. So I think it might be a good idea at this point, when you get to this point, you write your boundary conditions. So boundary conditions. So boundary conditions here, we have t of 0, y, that's on the x-axis, on the y-axis, equals 0, right? And t at 10 y here, 10, this is 10, and because it's the width is 10, and then anywhere on this line, the temperature has to be 0 at 10. So 10y equals 0. Right. Also, at x infinity, it has to equal 0 as you go way up, right? Away from this plate that has the temperature dependence. As you go infinitely far away from it, the temperature has to go to 0. So we also have t at x comma infinity equals 0. And at x comma 0, that's between 1 and 10, that's on the x-axis, the temperature is x. So the last boundary condition, this has to be x. Okay, now look, it's obvious if I want at infinity y for this to go to 0, sines and cosines don't go to 0 both at the same time, which means I need this third boundary condition when I plug in infinity for y for the temperature to go to 0. So I need the y part to be exponentials, because e to the minus infinity, or e to the minus infinity goes to 0.
Yeah.
Now, well, that tells me if this guy is going to take the exponentials, then I need to call this guy the k squared to get the e's, and this guy has to be the minus k squared because they have to add up to 0. And now I can solve both of these differential equations separately. This is called, this part in the process is called separation of variables. No?
Wait, wouldn't the y have to go to 0, so wouldn't that be the minus k?
Separation of variables. Say that again.
Isn't the y supposed to be minus k because it has to go to 0?
No, because look, when you solve this, this is a second order homogeneous differential equation. When you write the characteristic equation, if you remember, when the right hand side is negative, you will get the answers as complex exponentials, and those tend to go to sines and cosines.
Okay.
Because square root of minus k squared
Right.
will get you an I, and that will lead you to sines and cosines.
Right. So
The other one will get you the exponential.
Oh, okay.
You see?
Yeah. I think so.
Yeah. Questions so far?
Also, why is it d squared t dx squared plus d squared t dy squared is 0? Wouldn't it be and not d squared t dx minus d squared t dy squared?
Wait, say that again.
Why is it plus here and not minus?
Oh, don't worry about the minus and the plus, because I mean, like I mentioned to you, the minus and the plus will be determined by the boundary conditions. That's irrelevant.
Oh, but they are going to be different regardless.
Yeah, because they're a complete set of solutions. So eventually, they they will form a summation. Okay, so now I could go and do each one of these separately. So let's start with the first one. Yeah. So 1 over x d squared x over dx squared equals minus k squared. Okay, multiply both sides by big X, so you get d squared. This is a straightforward, basic differential equation. Move everything to one side, so you get d squared x over dx squared plus k squared x equals 0. Now you remember how to solve this, yeah? Characteristic equation. This will be exponentials, right? So you go to you assume y or x is equal to e to the mx. I mean, if you want to do it in detail, you could do that, but you could go directly to the characteristic equation if you remember. So c1 e to the mx plus c2 e m1 and 2x. And I'm not going to do the whole thing because this is basic, and so eventually you will you're not I don't think it's needed at this level of math to show all this. You just plug them in, so you're going to get, you go directly to your characteristic equation. So the first one will get you m squared, right? Because if you differentiate this twice, you're going to get m squared. Yeah. This is plus k squared equals 0. And then you just solve for m. This is called the auxiliary equation. You solve for m, so you get m squared equals actually, if you want to start this from the very beginning, you don't have to put these. You just assume it's, so you make this easier. You just assume it's e to the mx, and then you take first derivative, second derivative, etc., and then you get to the step. So this is m squared equals minus k squared. Take this square root, so you get plus or minus ki. Again, I won't go through at this level of math. I'm going to skip all the way, because when you plug these in, it will give you complex exponentials. And using Euler's formula, you can turn these into sines and cosines. So at the end of the day, you're going to, so I'll skip all these algebra in between steps. So then at the end, you will get x, right, equals c1 cosine kx. That's why we used k squared, so we don't end up with square root k here, plus c2 sine kx. So this is the solution. So this would be the solution of the first one. uh, where am I?
You mean the X term?
Yeah, the x term, exactly. So C1 plus C2 sine kx. Okay. Let's go to the y term. So the same thing will happen to the y term. So we have 1 over y. We call the first one minus k squared. So the second one will be k squared. So d squared y over dy squared equals k squared. And so multiply by y, you get d squared y over dy squared minus, I'm going to multiply by y and move it, minus k squared y equals 0. Again, this is a straightforward second order linear homogeneous differential equation. I'll skip the steps at this level of math. You can skip all that, go directly to the homogeneous characteristic equation or auxiliary equation, whatever you call it. So you will get m squared minus k squared equals 0, which means m equal plus or minus k. And the solutions here are assumed to be exponentials. So then you're going to get y is equal to, let's call these constants a, b, c, and d. A, b, c, e to the kx plus d e to the minus kx, because one of them is plus k and the other one is minus k. Okay, so this here is the second one. Okay, and so our answer will be this times this, because it's x times y. So this is y of y. So let's start putting in the boundary conditions. So I wrote them down. 1, 2, 3. We have 4 boundary conditions. Right? Now notice the third boundary condition tells you that as y goes to infinity, the temperature drops to 0. Which means, so I'm working now with the third boundary condition. So temperature goes to 0 as y goes to infinity. Wait, I made a mistake here. This is y, not x. Those are y's. Right. Okay, now look, the only way this can happen, if you put infinity here, this guy will blow up. The first term will blow up. So the only way this can work is if this guy is 0. You see? If C is 0. So that immediately tells you that C equals 0. And that modifies your y. So now the y is just d e to the minus ky. Okay? So now our solution becomes t of x comma y. It's x times y, so d e to the minus ky times x is sines and cosines, a cosine kx, right? Plus b sine kx. Okay, now look, when I multiply this, I'm going to get d times a, right? And when I multiply the second term, I will get d times b. So I can just absorb this d into the other two constants. I don't need to create another constant. So this will be enough, a and b. Okay, so far this is what we have. So far already.
And that needs the
Now we'll go to the other boundary conditions. So we've already used the third one. Yeah. This is also saying that when x equals 0, the answer should be 0. The first boundary condition. So let's do that. So let's go to the first boundary condition. So boundary condition number 1 says that t, what was it, x equals 0? Yeah, 0y equals 0. 0y equals 0. Well, plug it in, 0 for x, so you get t of 0y equals e to the minus ky. Yeah. Here you're going to get, for 0, this is going to be a, cosine 0 is 1, plus 0, cosine 0 is 1. And this has to equal 0, yeah? Well, think about it. The only way this can go to 0 is if a is 0. So that immediately knocks out another term. Usually that's the case. Every boundary condition would advance you one step towards the final solution. That's how it works. So, so a equals 0. So if a equals 0, that means I'm left with txy equals, now if this goes away, I only have one constant. I will call that, let's just call it b, whatever. b e to the minus ky cosine kx. Okay? Now, back to the boundary conditions. So we've used this guy, we've used this guy. We still have two boundary conditions. Now this is saying that at 10y, the temperature should go to 0. So let's plug that in. So t at 10y, so this is, I think, the second boundary condition, right? Let's use a different marker. So t at 10y has to equal to 0. Am I right on this? T at 10y equal to 0. Yeah, this is the second boundary condition. So plug it in again. So t at 10y is equal to, plug in 10 for x. So you're going to get b e to the minus ky cosine 10k equal to 0. Right? Now, look, this can only happen, this cannot be 0 except at infinity, and we're saying this is not infinity. This can only happen if b is 0. Now, if b is 0, then the answer will just be t equals 0, and that would be a trivial solution. That's not the one we're looking for. The only other way is if this is equal 0. So cosine 10k is equal to 0. When would cosine be 0? When 10k is odd or multiples of pi over 2.
Yeah. Odd multiples.
Right. Odd multiples of pi over 2, correct. So we will get 10k equals pi over 2, yeah, times an odd number, which could be 2n minus 1 or 2n plus 1, whatever you use, it doesn't matter. Let's use 2n plus 1. Okay, so divide that by 10 and you will get k to equal pi over 20 times 2n plus 1. Okay. Wait 1 second here. Whoa. I knew that something was wrong. The sine term is that what remains, not the cosine, because we said a equals 0.
Right, yeah.
This is the sine kx. Sorry about that. Okay, so that means this is actually
n pi.
Yeah, this is a sine here. I had a feeling something was wrong. So sine 10k.
Yeah.
And so this is sine 10k equals 0. Yeah, so this is all the multiples of pi. So this is just n pi. Divide
Wouldn't
that
it be
by
n
10.
over 10, yeah.
Yeah, so it'll be n over 10, n pi over 10. Okay, so now plug that back into this equation here. Let's call it C. So put that back in C, and we will get T x comma y equals b e to the minus ky, b e minus ky times sine kx. K is n pi over 10, so n pi over 10x. Okay, so we're almost there. Now, what's left is to figure out b. Okay, what's left is to figure out b. Now, there's one more boundary condition we didn't use, which is the last one. So we've used all these three. We still have t of x0 equals to x.
Right, yeah.
Okay, t of x0 equals to x. So that means
infinity.
Oh
no, wait, yeah.
no, because when you t of x0 will t of x0 oh, but wait 1 second. Now at this step, look what happened here. You've created an n, and n is any integer. N is 0, 1, 2, 3, all the way to infinity. So this is actually no longer a regular expression. This became a summation, because for every n, you're going to get a different b. And therefore, now your temperature becomes T becomes equal to a summation of the coefficients Bn, right, e to the minus ky, right? Oh, and we didn't replace this k with n pi over 10. So this is n pi over 10. Was it the minus? Yeah, minus, right? Because we said that c equals 0. Yeah, the minus one. So e to the minus n pi over 10. Okay, so now this became bn e to the minus n. Oops, go back to bn. N pi over 10 y sine n pi over 10 x from n equals 1 to infinity. So now this is a complete set of solutions, one for each n, right? One for each n. So now we go to the boundary condition, the last one. Now, of course, now the challenge is to find this guy here. And this guy is no longer one number. This is, you know, bn. B0, B1, B2, B3, etc. Huh? Yeah. Wait, is 0 included here? Let's see. 0 pi. Yeah. Yeah. Included. Okay. But if n is 0, this becomes e to the 0 becomes 1. So the answer here will be yeah. You could include that. That's fine. Okay. So now let's keep rolling. Now there's one boundary condition we have to use, which is the last one. Okay, t of x0 equals x. So the last boundary condition. So let's write this. So t x0 is equal to 10. So plug it in, and you're gonna get 10 equals, you're plugging in 0 for y, sum of bn, e to the 0 is 1, so this guy goes away, sine n pi over 10x equals to 10 from n equals 1 infinity. Wait, was it 10 or x? It was x, not 10. So the right hand side is, the left hand side is x, so this is x, and this is x. Okay, now you recognize this.
Yeah, that's
This is a,
solutions with Fourier series.
yeah, you could use Fourier series to determine these coefficients. You can use Fourier series to determine the coefficients, and the way to do that is we multiply both sides. Wait, where was Fourier here? Let me look up the multiplying factor.
That's Fourier chapter 7.
Chapter 7. So we need, yeah, we could actually, we don't need to, this is from Fourier series trick. Yeah, you could figure this out by, yeah, doing b of n equals the integral, right, of, and you can integrate this from 0 to L, and L is the width of the interval we're working with, yeah? So this would be 0 to 10, okay? 2 over 10, if you remember, it's 2 over L. F of x, right? Sine n pi x over L, and L is 10. So wait, let me just put this in L and then I'll plug in the numbers. So this is 0 to L, 0 to L. This is 2 over L. Okay. So, okay. Basically what you did is you multiplied both sides of the series by sine n pi x over 10. And you've integrated both sides. And when you do that, all these terms on the right hand side of the summation will vanish, except the one where sine is the same, and that gets you a L over 2. You move it to the other side, so it becomes 2 over L. You know what I'm saying? I'm skipping some steps here because at this level you've already done that. So I'm going straight to the answer. But basically that's what you did. It's called Fourier trick, right? You multiplied both sides by that, and then you integrated both sides. And the reason this is helpful is because all these terms in the series will vanish except one.
What's the thing?
And this guy here is gx 10.
Oh, 10.
That's just what we have here.
Right.
Yeah. Okay. So now plugging in the numbers, we will get bn equals, so L is 10 in our case. So this will be 2 over 10, integral from 0 to 10. F of x is just x. F of x is x because because t is x. Right. Okay. X sine n pi x over L dx. And L is 10. Okay. Okay, integration by parts. We have polynomial times sine. That's just integration by parts. You can see it's a long problem. These are long problems. So integration by parts. So by parts. By parts. U is x, and dv is sine n pi x over 10. So du is dx. And v is integral of sine is minus cosine, so minus 10 over n pi cosine n pi x over 10. Chain rule gets you that factor of minus 10 over n pi in the v. So then bn becomes, so 2 over 10 is just 1/5. Alrighty. We have uv. So uv will be minus 10x over n pi cosine x cosine n pi x over 10 minus integral of v du. So minus and minus, this becomes plus 10 over n pi. I'll leave it outside because it's a constant. Cosine n pi x over 10. And we are integrating this from 0 to 10. And this whole thing, when we're done, will be evaluated from 0 to 10. So bn will equal 1/5. Okay, minus 10 VDU. How about I take out, the more simplification you do here, the easier the problem is. So I'm gonna pull out a, or actually, I'll pull out, yeah, I'll pull out now 10 over n pi. Okay, so I have left minus x cosine n pi x over 10 plus 10 over n pi, and the integral of cosine n pi x over 10 is 10 over n pi, chain rule, and then sine, the same thing, n pi x over 10. And now we will evaluate this from 0 to 10. Okay, so bn, this will become 10 over 5 is 2, so 2 over n pi. Plug in the upper bound and the lower bound, so 10 will be minus 10 cosine. If you plug in 10 here, you will get n pi plus 10 over n pi squared. If you plug in 10, you will get sine n pi. Sine n pi is 0 because that's multiples of pi.
Yeah.
Okay, minus, done with this. Now plug in 0 here, you will get x cosine 0, that's just 1, minus, so minus minus. Actually, let's put another bracket so we don't get the signs confused. So that's minus x. And then here, if you plug in 0, sine 0 is 0, so this whole term will go away, so you're going to get minus 0. Okay, and so simply this turns out to be a fairly simple expression. 2 over n pi times minus 10 cosine n pi, right, plus x. Plus x. Oh, plus, wait, we didn't plug in for x, what it is. X is 10, right? Because this was the upper bound, so it was, the x was 10. Okay, so plus 10. Okay, factor out the 10 outside, so you will get 10, 20 over n pi right? You have left 1 minus cosine and pi. Okay, now what's cosine and pi? Well, it depends on what n is. If n is even, you will get even multiples of pi. Even multiples of pi will get you cosine will be 1.
Yeah, it will be. Yeah.
1 minus 1 is 0,
Right.
so this whole thing will be 0
Right.
if n is even.
And if it's odd, it'll be 2.
If n is even, right?
Yeah.
And yeah, if n is odd, you will get minus 1, so this becomes a 2. So 2 times 20, this will become 40 over n pi. If n, the 0, oh, because the first one has an x. Yeah. The 0 will make the first one go away. This is 0. Yeah, I'm sorry. We made a mistake here. This is the mistake. So this is 0. This was an algebra mistake. So then we just get, so this whole thing goes away, and we get minus 10 cosine and pi. So let's erase this. Okay, so then this is just 2, and this will be, right, minus 20. Because it's minus x. Yeah, okay. So this will be cosine and pi. Now, if pi is even, if n is even, this will be positive and positive 1, and we will get minus 20 over n pi. If n is even, right? So if n is even, yeah, we will get that. And if n is odd, this will be 1. This will be minus 1, but there's another minus sign here. So this will become 20 over n pi. Positive 20 over n. So let's summarize this. We can actually write this explicitly as 20 over pi times n times minus 1 raised to the n plus 1. And what this minus 1 to the n plus 1 is, makes it alternating series. So if n is odd, this becomes even, and this whole thing becomes 20 over n pi. And if n is even, this becomes odd, and this becomes negative 20 over n pi. Bingo! We've determined our coefficients. We're almost there. These are the bn's. So if n is 1, you will get 20 over pi times minus 1 squared will be 20 over pi. If n is 2, etc., so on and so forth. So now I can plug this back into my function, which is the temperature here, yeah, in the green one, because I've determined my coefficients. So let's say plug this in D. So plug in D, and finally my final answer will be T of x comma y will equal the summation, right, of Bn. Now anything that's constant, I can take it outside the summation. So this is 20 over pi from n equals 1 to infinity, because all n's are included, minus 1 to the n plus 1 divided by n. I already have the pi here, so that's my b's of n, right? E to the minus n pi, right, y over 10 times sine n pi x over 10. Bingo. This is the final solution to Laplace's equation. which matches this answer. You see how to do this problem? There's a lot of steps.
Yeah.
But this is very important. This is almost guaranteed on the exam.
Right. So,
any questions on it?
I just want to try doing the first part of one of these.
Sure, which one?